hypolimnia, I put snow from outside in the water, it's cold. Then this was just, the red was just regular tap water. And then the green here at the surface where the algae is growing, right? Get it? Was hot water. All right, as hot as I could get it out of the depth. So we have thermal stratification in there. And now, I better move this. Let's take the screen up. I make a mess doing this. All right, in the 3-hour version of the lab, we put fans on it and very gentle. We don't have time for that, so the faster wind. Okay, so you can begin to see how it's depressing that in. All right. Increase it a little bit. All right. Now we've got colder water up here, and it's going to probably look and see. So we're down to about here, and then if we wait just a little bit, this is going to rock back and forth because we've got potential energy. Crazy. All right, so now our hypolimnion, I didn't point this out before, the hypolimnion was started about here before. Now we've raised it here. So on an equivalent scale, we're probably beating Lake Ontario, right? Right. So now the waves moved up over there. Right? Our epilimnion is down to here or so. Okay. We'll do that again. All right. Oh, too much. Overdid. All right, so here's our block of warm water. We've got some caught in here. Yeah, I definitely overdid there. But you can see pretty rapid flow. I don't know if you can see from back there. There's some particles in there. In fact, let's do a little. Here's some powder dye. They'll drop. So you can see the complex movements perhaps, or at least I can see this dye over here is moving this direction, right, at the surface, still captured, and some of it is moving down. Now we've got what I was trying to show, and I don't know if you need to get closer. I don't know if you can see from over there. But you can see the complexity of the internal movement, all right? So water down here, these little trails, I don't think you'll be able to see on the video, but water down here is moving this direction. You can see these little dye trails going this way. All right, here's one going down. All right. All right, another thing we can demonstrate with this is what happens if a cold river flows in. And I hope I didn't mix this up too much. All right. So, and this is something we studied quite a bit up in the Sawtooth. You have cold mountain stream water coming into fairly warm lakes. It might be 20 degrees centigrade swimming temperature at the surface. Not warm enough for you to swim? All right, but the stream water might be 6, 8, 10 degrees. All right, so what happens to that when it flows in? And I don't know, my colors aren't so great anymore here, but I've got some blue dye, and we'll working. So it's going down, it goes down. Two things happen. When it goes in and when a stream comes in, it actually entrains or mixes, the cold water mixes with a lot of the surface water. So you get something of intermediate density, all right? And then it'll go down, and it almost always interflows, okay? Interflow, I don't have a marker, but that's a term you'll want to know. And it interflows usually near the top of the metalimnion because you've mixed warm water here with some cold water here, and it goes down. At times, if conditions are just right, you can have densities, it'll flow all the way to the bottom, all right? If, for example, you had, let's say in the spring, 3-degree water, 2-degree water coming in, it's mixing with 5-degree surface water of a lake that's just beginning to warm up, it forms 4-degree water, it's going to go all the way down to the bottom, right? Most of the time in the summer we get these interflows, all right? All right. Not quite wide enough, dude. It bows. So in the fall, okay, the lake's starting to cool off, right? Loose heat, back radiation, conduction to the cold air. So the density layers are getting closer and closer together, right? So it's easier for the mixing processes and some of this entrainment to, as layers slide over, you get vortices. That's what we're going to talk about on eddy diffusion. And you start mixing things, and you get to a point that maybe that you've got 8-degree water here or 6-degree water here and 4-degree. Then it becomes easier to depress this, right, because they're closer together in density and buoyancy. And you start mixing. So in the fall, you get quite a bit of your mixing occurs as a result of it. So we'll do that. Uh-oh. My scuba tank's out. I chose one that was already mostly used. So maybe we won't, I wasn't watching. When I'm in the wind, I can't see things. Okay, so we'll put a little more dye in, see what our current patterns might look like. And if you want, come on, go down, guys. I don't know how much you can see from back there. But I need more different colored dyes. I think maybe we're still stratified here. But by mixing red and yellow and green together, it's all starting to look the same, and so we're losing our ability to see things very well. Another thing you can sometimes see when you do this is when it was stratified that things fall faster through the epilimnion and then slow down when they hit the hypolimnion. I don't know if that was detectable before. Why would that be? Why would they slow down? Density difference, but what's it mainly affecting? Yeah, we've got a current going. More higher viscosity, and it slows down particles that are sinking. Right, so a phytoplankton cell sinking will fall a lot faster through the epilimnion than through the hypolimnion. All right. You can see the water sliding down, moving along here. I don't think we've mixed it all the way to the bottom. Yeah, maybe have. All right. Okay. So it makes for a rather nice demonstration of some of the process. It doesn't really show the surface sesh, or at least the way if you put just a fan on it and have a millimeter scale, you can actually detect the surface sesh too. But with the big blow, the surface waves overcome those subtleties. But you can definitely see how big and how pronounced surface seshes are, and they're very important in a lake, but they go on sort of, you don't notice them unless you put a thermistor chain in or things. And particularly then when those currents intersect with the bottom here. Let's see if we can do that. I'll put a little more wind on here. I've got some, can you see from that angle on this plastic sheet here, some of those dye particles are laying there, and they haven't, I guess I'm out of wind, aren't I? Okay, the alternative. Okay, so that wave depressed, we're getting entrainment and turbulence in here. All right. And I don't know if it'll flow back and hit this die at this interface or not. I can certainly make it do that. Uh-oh. The bottom of earthquake. Oh, well, that didn't work. I was going to tape that up there. I forgot about that, doing that. Okay. But you can still see, the wave, and, that'll reach equilibrium. They move pretty slowly. We'll talk, whereas surface seshes take, in Bear Lake, like hours, internal sessions move a lot slower. So can be days. While we saw the Lake Ontario, what was that period? Maybe, 7 days? Well, it had several cycles over the 5 days, but it was about a day, I think, was the period of that internal sesh. We can look at that graph again. Okay, questions? Okay, have a good weekend.